welcome to this lecture on sound barriers in the course on noise control in mechanical systems. So, here in this lecture, we have started the discussions on passive noise control. Okay. So, we are doing passive noise control, and then we have studied about the concept of acoustic materials or the materials typically used to control or manipulate sound waves through them and how they can be used for passive noise controls, and a broad sort of classification of these acoustic materials are as barriers, okay, and as absorbers. And barriers are the materials that sort of minimize the transmission through them. So, we already discussed about the sound barriers and what are the typical performance measures of these sound barriers, and then today we will discuss about one more performance measure, which is the sound transmission class that is assigned to various barrier partitions. Then we will study the working principle of a typical acoustic barrier and the mathematical formulation of the performance of an acoustic barrier in a particular setup. So, let us see. So, to quickly say, the performance of the sound barriers can be evaluated using these various kind of measures. We have the sound transmission loss, insertion loss, noise reduction. All of these are not a single value, but they are all functions of frequency. Okay, it is not a single value measure. These are functions of the frequency, therefore, they are not a single value measure. Now, in today's class we will discuss about the fourth kind of performance measure, which is the sound transmission class, and this sound transmission class is a single value measure. Okay. So, based on how is the 1/3 octave spectrum obtained by when the sound wave passes through this one kind of partition and the kind of transmission loss spectrum that we get, we can compare it to some reference contours to finally get a single value which gives you the sound transmission class, okay, of that particular barrier partition. So, let us see sound transmission class or STC. It is an integer number that rates how well a building partition attenuates the airborne sound. So, here just remember that it is typically used to find out how it is attenuating or reducing the airborne sound. The structure borne sound is not taken into consideration here. The TL curve of the material. So, what happens? You first obtain the transmission loss to that particular partition wall, and you find out how much is the transmission loss from that particular material, and you plot it in the octave spectrum against the frequency, and then just like we had the noise criteria curves, we had the NC, NR, RC and the NCB curves, where a set of standard contours were there, and the octave spectrum of a space was compared against the standard contours and a single number rating was given. In the same way, the TL curve is obtained, and then it is compared with some standard set of sound transmission class contours. Okay, these are the standard contours, and the closest matching contour will determine what is the STC rating of that building, of that particular material. So, this shows the family of the STC curves. Okay. So, here whatever the curve has got a standard shape, the first part of the curve starts from this is in the octave spectrum, sorry, it is the 1/3 octave spectrum. Over here just a small correction, please note this is 1/3 octave spectrum, and in the 1/3 octave spectrum, starting from the middle frequency of 125 Hertz to about 400 Hertz, the curve follows a slope of 9 decibels per octave, and in that slope you have a straight line curve. Okay, so, it is a straight line with a slope of 9 decibels per octave in this region, and then from this onwards 400 Hertz till 1250 Hertz, the curve follows again a straight line with a slope of 3 decibels per octave. and then followed by that, from 1250 to 4000 hertz, the curve becomes a flat line, the slope becomes 0 decibels per octave. So, all the curves, they will have the same shape, one sloping, one steep line 9 dB per octave followed by the 3 dB per octave and then a flat line in the 3 frequency regions. And what is the, so these are the reference STC contours or STC curves, and the value associated with the reference curve is the value where that contour is crossing the 500 hertz octave frequency. So, over here you can see this particular curve here, it is exactly at 500, the value of the the value of the STC is 20. So, we give it a value of STC 20. Then the same curve 9 dB per octave, 3 dB per octave and 0 dB per octave, these lines you plot one by one, you can plot it, and whatever value it achieves at 500 hertz becomes that STC number. So, here you can see 30 decibels, and then here this curve 40 dB is the value at 500 hertz. So, it is assigned STC 40 and so on, STC 50 and 60 and so on, and in the middle of them, as in you can have infinite number of STC contours. So, you can have the STC 21, okay, following the same pattern, STC 22 following the same pattern, which means the same slopes in the same defined frequency regions and so on. So, there can be many such STC curves, all of them following the same kind of slopes in the predefined frequency region, and whatever value comes based on this shapes at the 500 hertz becomes its STC number. So, I hope with this description it is clear how to obtain the standard STC curves. Okay. You simply draw a line from 125 to 400 and the slope of the line should be 9 dB per octave followed by a line from 500 to 1250 with a slope of 3 dB per octave and so on, and you can keep drawing such lines at any point. So, infinite such lines which are a family of the STC curves. So, now how do you now determine the sound transmission class, typical class of a material or a partition? So, it is usually used to sort of characterize and rate a partition wall in a building. So, let us say you have got one room where you have a microphone and another room. So, this is called as the source room. Okay. In this room you have this reference source which is generating your noise, okay, and then you have a partition. So, you have some standard dimensions, you can refer to the ASTM standards for finding out how the STC or the sound transmission class is determined. So, you have a room which is a source room where you play the noise source, and you have a speaker here, and then a partition wall, and then the other room, all the other walls are made of the same material which is supposedly acoustically hard, and only this one is the barrier material that has to be tested, this wall here that has to be tested. Okay. And then you have a microphone here to measure, and so that the sound intensity level measured here before the material, and you have the sound intensity level here, and based on the two measurements you can find out the transmission loss due to this particular partition. So, once you obtain the transmission loss by testing a particular partition in this manner, you pass the sound waves, you measure the sound pressure level before you and the sound pressure level after passing through the material, and compare those values to get the transmission loss. Then after that what you do is suppose let us say you obtain a particular transmission loss curve, this is your transmission loss curve for the tested material, and now you know that there are various such standard STC contours like this. Okay. So, you start from the STC 0 value and you keep going up. Okay. So, you start from the STC 0 and then you keep going up till you reach a contour. Suppose I reach finally this contour, Okay. So, till you reach a contour where what happens is that this condition is satisfied, that finally the total decibel of all the frequency bands in the test curve that are below the reference contour, they should not exceed 32. So, let us say finally you start drawing these various curves, and what you get is, let me get to a single contour just to show you. Okay. So, let us say you started drawing the various contours and you finally reached one reference contour where this is your reference contour. Okay. So, here what should happen is, the total dB of all the frequency bands in the reference spectrum that are below it. So, these areas, okay, these areas over here which are below it. I think it is better to draw a different reference spectrum that makes it look more believable. So, let me draw once again the TL spectrum of a material, and suppose you start drawing the various STL contours, and finally you go up from STC 0 and you go up in steps, and finally you reach one particular contour where suppose it looks like this. Okay. Let us say, and the very first contour where this condition gets satisfied, that the net decibel total below it is less than 32 dB, and the net decibels above it, the total, you sum up these dBs, so you know how to combine the decibels, you combine them, decibel combination is something like this. 10 L equivalent is 10 log 10 of L1 by 10 plus 10 log 10. This is how you combine the decibels. So, when you combine the decibels, the total decibel that are below must not exceed 32, and those above, and no point on the test curve and no point that is above. So, the maximum value of this difference, the point that is above, should not be less than 8 dB. Okay. The maximum point on the test curve which is above the reference STC contour, this value here, it should not exceed 8 decibels, and all the points that are below, they should be smaller than 32 decibels. So, the very first curve that achieves this condition then becomes, then that STC value, the STC value of this curve becomes the STC rating of the barrier material that you are testing. Okay. So, let us see, for example, this is the measured transmission loss of a partition wall where this kind of a typical test environment has been used, and this is the measured transmission loss. Now, you can start by drawing the various STCs from STC 0, STC 5, 10, 15 like that, various kind, and let us say at a certain point here STC 20, the net values here, the dB total which is for the curve which is so the dB total of all the frequency bands on the test curve that are below the reference contour, which are these values, the net, the dB total of all these things should be smaller than 32 decibels, and this is the highest value which is above the reference contour. The difference between them, okay, is less than 8 dB. So, the closest curve that you get becomes your STC 40, the very first curve that satisfies this. Again, this is 1/3 octave frequency, alright. So, this is how you assign the STC 40 to this particular partition wall. So, some of the STC recommended, I will just say this is the STC, not recommended, but the measured STC ratings of different partitions and walls. Now, just remember that when you are using a particular material, the transmission loss achieved at the material depends on a lot of properties. It depends on what material you are using, and at the same time what are the dimensions of the wall, what is the thickness, length and the breadth of the wall, and how the wall is mounted, what are the end conditions or support conditions of that wall. So, whenever the STC rating of a particular partition or wall is given, then the thickness is first of all the material that is used to make it is specified, then the thickness is also specified, and how it is mounted or what are its boundary conditions at the edges, they are also specified, and that completely gives you that this is your particular partition and this becomes your STC rating. So, these are the various things that you can look at, it can be found in the books. Okay. And so on, you get the material with its specific density, thickness and the way it is mounted, and you get the STC rating. So, you have the STC tables available with, so any noise control engineer usually you can buy a handbook on noise, vibration and control, and in these various handbooks always these standard tables are available. So, as a designer you can choose the best STC partition for your building. Okay. So, now the sound barrier materials, they can be used for a lot of things. They can be used to make the walls, ceilings and the floors and the various partitions in the buildings. They can be also used as acoustic reflectors in the pathways for some experiments, and they can also be used as enclosures. Okay. So, what is meant by enclosures? Let us see. So, before that let us see the working principle of outdoor acoustic barriers. Okay. So, whenever the barriers are used indoor. So, in the indoor what happens that the barriers, they are effective in reflecting back and blocking the direct sound field, but if suppose it is a very highly reverberant environment and there are so many sound paths through which the sound can reach the receiver, then in that diffuse field environment the performance of the barrier essentially reduces, because it is a partial barrier. So, therefore, more barriers are usually used in the outdoor environment and not in the indoor environments. In the indoor environments we use the enclosures, in the indoor environments they can be used, but barriers are usually used in the outdoor environments. Okay. So, because they are ineffective in blocking these reflected sound fields when there are infinite number of paths through which the sound wave can reach the listener. So, what is the working principle of these outdoor acoustic barriers? First is diffraction of the sound waves that happens over the edges of the barriers, then the reflection of the sound waves from the surface of the barrier, the transmission of the sound waves from the surface of the barrier, and the absorption of the sound waves on the surface lining. So, the sound waves are hitting, they are diffracting back from the edges, they are reflecting back from the surface, and then whatever is remaining, it gets transmitted, then some part of it gets absorbed and dissipated, I would say, while passing through the material of the barrier. Okay. So, let us see how the performance of an outdoor acoustic barrier is evaluated. So, typically a barrier is placed in an outdoor environment. So, we have some let us say this is your receiver, this is some noise source machinery, and you want to block its pathway using this barrier, and this is how the sound is moving, so that you can create some shadow zone. So, in the outdoor environment there are various things such as first of all, when the sound wave is propagating, if it is a point source, it is propagating as a spherical wave front, then with the distance anyways the sound is spreading and following the inverse square law. Attenuation happens due to the absorption within the air itself, then the wind and the temperature gradient conditions can vary from time to time. Diffraction can happen from various things like trees and other objects that might be present. So, there are so many things outdoor, it is not a controlled environment, and there are so many things that can lead to absorption or attenuation of sound. So, how do you evaluate just the performance of the barrier when there are so many other things that are distorting the sound wave? So, the best measure could be used is the insertion loss. So, you first measure that without the barrier, this was the typical sound levels at the listener in the presence of all these other effects as well, but then the barrier is added, this is the reduced sound pressure level at the receiver. So, here from this you can directly get the sole contribution of the barrier in that setup. So, this shows typically a receiver, so let us say you have some source which is generating the sound waves, and whatever they are going to reach the receivers, they have been blocked by the barrier. So, any of the direct sounds that were about to reach the let us say this is the receiver's ear. Okay. So, a sound in the absence of barrier would have reached the receiver following a path of length. So, here the path length is equal to d when barrier is not present. So, when the barrier is not present, the shortest path length taken by the sound wave would be d, and given that it is a spherical sound wave, with the increase in the distance, the overall pressure is going to go down following the inverse square law. That means that the pressure would be inversely proportional to the distance for a spherical source. So, if the shortest path length was d if the barrier was absent, but now that the barrier has been installed, what happens is that now the sound at the d is not being received, rather the direct sound that is reaching the receiver is the shortest route taken by that direct sound wave is this a plus b. The new shortest path length, I would say, I would add the word shortest. So, this is the shortest path length in absence of barrier, which is d. The shortest path length in presence of barrier, over here it is installed in the ground, is now a plus b, which is definitely much greater than d. Okay. So, the path length is increased. So, that is why some attenuation is happening because of that. So, there is some attenuation because the increase in the path length of the direct sound that is reaching the listener, as well as anything that is going there, it is suffering some attenuation through the material itself. So, there is some loss due to the transmission loss of the material itself. So, overall the derivation is again not in the code. So, directly we come to the mathematical formulation. So, the insertion loss for an outdoor acoustic barrier, it is given by 20 log 10 of a plus b by d plus 10 log 10 of 1 upon c d plus tau. So, here what are these various quantities? So, the insertion loss, the first kind of loss happens because of the increase in the path length. So, here a plus b is the new shortest path length where the sound is directly reaching without being blocked by any material, and previously it was not a plus b, but it was rather a shorter path length d. So, a plus b by d. So, this is the attenuation due to the increase in the path, and then there are some attenuation due to the diffraction that is happening around the edges, and that is given by a diffraction coefficient of the barrier, which is a function given by this, it is a function of the frequency. This is called as the Fresnel number. All of these derivations have been long derived and are not within the course. So, here n is the Fresnel number, and whenever the n value is smaller than this, so at lower frequencies this is the kind of the diffraction coefficient, and at higher frequencies beyond a certain value it becomes a constant of 0.004. And then there is also some attenuation due to the transmission loss within the material due to the presence of the material itself. So, that also is accounted for here using this tau factor. So, these various factors come together to give you the net insertion loss. Again, these are some of the equations that a noise control engineer should definitely remember. Okay. So, from these equations what you see is that, see, if this quantity, suppose everything else is fixed, a and b, they are dependent on the dimensions of the barrier. So, if you increase the height of the barrier, the a and the b both are going to go up. Okay. So, a much larger path difference will result. Therefore, this quantity will increase, and hence the overall insertion loss is going to go up. So, the higher the height of the barrier, the greater will be the insertion loss. Now, what about, and similarly if you are using a material with a higher transmission loss, so this means that if you increase this value, then this overall quantity decreases, Okay. Sorry, if the transmission loss is increasing, which means tau is decreasing, and hence this value is increasing, so IL is also increasing. So, with the increase in the transmission loss of the material also, the insertion loss increases. With the increase in the height of the barrier, this quantity increases, so the insertion loss increases, and with the frequency also, because at lower frequencies this number is small, at higher frequencies it increases. Therefore, at higher frequencies, when this value is increasing, this is going to decrease. Sorry, the other way around, at higher frequencies this value is going to decrease, this is going to increase, and hence the overall insertion loss is going to go up. So, basically insertion loss will increase with the increase in the sound source frequency, because with the increase in F increases. So, basically F increases, then the Fresnel number N increases, and the diffraction coefficient for smaller frequencies given by this sign thing, and then for larger frequency it sort of, so this CD value, it is a fixed small value for higher frequencies, but for larger frequencies it is a much higher number. So, the CD overall goes down, and when the CD goes down, then this second kind of term increases in value. So, the overall IL increases. When the barrier height increases, A and B increase, and therefore, the first term increases in the transmission loss calculation. So, the overall transmission loss increases, and when tau transmission coefficient decreases, again the second term it will increase. So, when the TL is increasing, the tau will decrease, second term will increase. So, overall the insertion loss is going to increase. Now, usually the barriers, one of the most common applications of outdoor barriers is in the use of highways, where they are installed next to the highways to block the sounds from propagating further into the nearby market areas and the residential areas. Okay, these kind of these can be in the form of cement walls, fences, earth berms, dense vegetations, buildings, or various such combinations. So, you can see along the highways, these kind of, even the trees and the plantations, the cemented barriers, and all these kind of various kind of complicated barriers as well. They are there to block the sound waves. And for this typical highway barrier, this is an empirically derived relationship, that in the highway barrier the insertion loss is given by this formulation. So, a small change from the general outdoor acoustic barrier. Okay. Fine. So, with this I would like to close this lecture. Thank you for listening.